Now, without further ado, I'm honored to introduce our first keynote speaker of the day, Dr. Fei-Fei Li. Dr. Fei-Fei Li is currently Chief Scientist of Artificial Intelligence and Machine Learning at Google Cloud. Also, she is an Associate Professor in the Computer Science Department at Stanford, and she is the Director of the Stanford Artificial Intelligence Lab, as well as the Stanford Vision Lab. Dr. Fei-Fei Li's main research areas are in machine learning, deep learning, computer vision, and cognitive and computational neuroscience. She has published more than 150 scientific articles in top-tier journals and conferences, including Nature, PNAS, Journal of Neuroscience, and many more. Dr. Fei-Fei Li obtained her BA Bachelor of the Arts degree in physics from Princeton in 1999 with high honors, and her PhD degree in electrical engineering in Caltech in 2005. She joined Stanford in 2009 as an associate professor and was promoted to as an assistant professor, and she was promoted to associate professor with tenure in 2012. Dr. Li is the inventor of ImageNet and the ImageNet Challenge, a critical large-scale dataset and benchmarking effort that has contributed to the latest developments in deep learning and artificial intelligence. In addition to her technical contributions, she is a national leading voice for advocating diversity in STEM and AI. She is co-founder of Stanford's renowned Sailors Outreach Program for high school girls. Now please join me in welcoming Dr. Li to the stage.
Good morning, Harker students, parents, colleagues, and everyone here. It's a real honor to be here. When Amy said that they spent a month preparing for this symposium, they were really not kidding. I think my invitation, they sent the invitation almost a year ago and has since then been, really checking in every other week about if I'm doing my homework. So a lot of effort has been put into this symposium. It's a true honor to be here. Here's what I will do. I'll spend a little bit of time giving you an overview of computer vision and what we have been doing the past few years that I'm titling The Quest for Visual Intelligence. And afterward, I would love to welcome audience questions through the setup that Amy and her colleagues have put up. So I would love this to be more interactive than just me talking. To begin with, I want to share with you a little bit of the recent progress in the field of computer vision. And to have a historical point of view, let's go back to 540 million years ago. 540 million years ago, what is the Earth like? Well, it's mostly water. All the animals we knew were living in the waters. In fact, there aren't that many animals. It was a very simple life. What evolutionary biologists call is very few species were around. And animal kingdom was simple. These trilobite-like water species just float around. When the food comes by, they grab it. If it didn't come by, they just chill. So very, very simple. But then a very mysterious event happened around 540 million years ago. And this is what people call the Cambrian explosion, or the Big Bang of evolution. Within 10 million years, and that is a very short period of time in terms of evolution, the number of animal species just exploded. We suddenly get a huge increase of the different numbers of animals. And this came out of our fossil studies. And biologists were wondering about this for a long time. Why suddenly a small number of animal species just exploded? What was the driving force for this explosion? A lot of study have gone into this, including climate changes, Earth's own change of environment, and other reasons. As it turned out, there was a young Australian evolutionary zoologist. His name is Andrew Harker. Not long ago, he did extensive fossil studies and found out that precisely around 540 million years ago, the first animals developed eyes. And at that time, the eyes are really simple. It literally is a little bit like the pinhole cameras. It's just a hole that collects some lights. But that very onset of vision changed the entire animal world. Now, life is active and proactive. You can actually seek food. Imagine the first animal that developed eyes. The entire world is like a giant free buffet. You can just go and grab any food you want. But quickly, animals start speciating because if there are predators coming to catch other animals, well, the prey also have to develop eyes and start hiding from the predators. So it's the onset of eyes that started what the biologists call the evolutionary arms race of speciation. Animals suddenly develop all kinds of tricks in order to find food as well as to escape from being somebody else's food. So since 530 million years ago, vision played a critical role in the evolution of animals, from navigation to food seeking to manipulation to more. Here I'm just showing you some example eyes that animals have developed. Of all the animals, of course, the most special one is humans. Humans, it took 540 million years for evolution to deliver the most intricate and functional visual system that the world has seen. So humans not only use vision for survival, for seeking food, but we use it every day for understanding the world, for communication, for entertainment, for work, for discovering, for many things. So the picture right there is actually my daughter. So every time I look at her eyes, I just can't help to think how beautiful they are. So vision, after all these years, vision has become the largest sensory system in the brain. In fact, I don't know if you know this, half of our brain, more than 50% of our cortex is involved in visual processing. It is the largest sensory system, and it is part of the cornerstone of human intelligence. So while animals have seen the light of the world 540 million years ago, our machines and computers still have a long way to go. We're still very much in the dark age. While a lot of progress has been made, but still we haven't delivered vision as a ubiquitous technology to help human society. For example, we haven't delivered vision mostly to our visually impaired fellow people. A lot of cameras are out there in the world, but we haven't been able to have a ubiquitous technology to help kids, to prevent kids from drowning in swimming pools, or to survey the giant land of the earth in order to give us data and information on the environment or development. Or in specialized areas like healthcare, vision can potentially play a ginormous role in helping doctors to do diagnosis and help our patients. So, but in the same time, visual data is one of the most prevalent data in our digital world. You probably wouldn't be surprised if I tell you that hundreds and hundreds of hours of YouTube videos are uploaded to YouTube every single minute. And there's no way humans by ourselves can go through these videos and harness the content. Or another statistics is for the past 30 days, humanity has created more digital images than the entire human civilization have created before 30 days ago. So think about your Snapchat pictures that all the students are taking. Or Cisco has estimated by 2016 last year, more than 70%, 75% of the internet cyberspace data is in the form of pixels. So harnessing visual data, enabling computers to be able to perform intelligent visual tasks is one of the most important goals of the field of artificial intelligence. And put it simply, computer vision is about shining light to the digital world that is full of pixels. So just a word of clarity. I know a lot of you sitting in the audience have heard the terms like AI, artificial intelligence, machine learning, computer vision, speech recognition, deep learning, robotics. What are the relationship between these terms? Here's my view. At Stanford AI Lab, we treat the whole field of artificial intelligence as a quest to build intelligent machines. And AI was born 60 years ago. Since then, the field of AI has proliferated and evolved into multiple subfields. And within each subfields, we have slightly more focused goals, but they all contribute to the global quest of intelligent machines. Some of the subfields you hear about are machine learning, focusing on statistical modeling of data, computer vision, focusing on, this is the rest of today's talk, enabling machines to do visual understanding. Natural language processing is to build machines and algorithms that can read and communicate like humans. Speech recognition is to build algorithms and machines that can understand speech and turn it into text. Robotics is also as old as AI, which is focusing on building physical machines that can move and manipulate and navigate. But all these fields today are interconnected and have become part of the larger field of AI. And within machine learning, you hear a lot about deep learning. That is a recent development of the research from machine learning that focuses on neural network research. So I thought that it would be good to clarify these terms. All right, so let's continue to look at how we build visually intelligent machines. So the first step towards teaching a computer to see is really enabling the ability of object recognition. Object is the fundamental building block of the world. If you look at early development of babies, my daughter is around 14 months. This is precisely the time she's learning to see objects and giving names to them. And this is what we want to enable machines to do as a first step. So imagine this is the teaching process to the machines. We want to show computers some examples of a object, say cat, and then the machine, we design a mathematical model that can learn from these training images during the teaching phase. And eventually, the computers will learn, and then when you show it a new picture of cat, it'll say, oh, this is cat. That's what we call object recognition in computer vision. And humans do this so effortlessly. I don't think anyone in the room would even think about how you do object recognition. You just do it. So this is what we thought computers would do. How hard is it to recognize any object or a common object, for example, a cat. Well, a cat is kind of a combination of geometric shapes, right? So in the early days of computer vision modeling, that's what we did as vision scientists. We built models that are consisted of these shapes that we see cats are consisted of, such as round, ellipse, triangle, or blob, and so on. And then we configure these shapes so that they look like cat. Well, that sounds very simple. But then what about a cat like this? The model we have just learned of that nice canonical cat will no longer apply. So then we have to go and build another model for a different cat. Well, there are many, many cats in the world, especially on the internet. And if you want to start building specialized models for cats, and especially to accommodate the endless variations of an object, you're suddenly running into a problem that is infinitely complex. It's really hard to scale. And we actually, as a field, in the early days, in the 80s, 90s, early 2000s, that's what we were doing. We were exploring different ways of hand configuring models for different objects. And it was a very difficult process. We made progress, but it wasn't where we could deliver these algorithms to the real world application. So something else needs to be done. About 9 years ago, I started as a assistant professor actually at Princeton. And I was thinking there's got to be some other ways of teaching computers to see. And observing how children learn was my inspiration. And nobody tells a kid, especially later I have my own kids, I realized you don't tell a baby, oh, let's look at a cat. It has a round face and the triangular ears and all this. Nobody says that. The babies, the humans and animals, they experience the world just by sheer experience and experiments on their own. If you think about our eyes as a pair of biological cameras, it takes a picture about, or two pictures, about every 200 milliseconds. That is the time your eye makes a small movement called eye movement or saccade. And so in that kind of computation, a pair of eyes take 5 pictures per second. And if you think about a baby's life from 0 to 3, she would have taken hundreds of millions of pictures. Of course, there is continuity. We can talk about it later. But that's the sheer volume of data that babies get in their early development. Instead, before we realized that, our field of computer vision was showing computer algorithms a few dozens or a few hundreds of pictures, and was hoping that the computer algorithm can learn something that babies eventually were able to do. So I thought that let's take another view. Instead of just focusing on the algorithms and keep hand-tuning the parameters, let's take a big data view. Let's take a view that's biologically inspired and give computers the kind of data in both quantity and quality that humans experience, and drive the learning algorithm through that kind of data. So around 2007, my colleague, Professor Fei-Fei Li, and student Jia Den, who is now a professor at University of Michigan, Ann Arbor, we started this ImageNet project. And now the rest is history. We went to the internet and downloaded billions and billions of images, and used a very early at that time technology called crowdsourcing, the Amazon Mechanical Turk platform, and build a data set that was bigger than thousands of times bigger than any data set the field of artificial intelligence has seen at that time. And it's the ImageNet data set of 15 million images categorized around about 22,000 objects and sceneries. And that was the beginning of a new wave of object recognition in computer vision and machine learning. So the take-home message so far is that we were inspired by the way children learn, and we were inspired to think of learning as a big data problem around 2009. So as it turned out, the wealth of information provided by ImageNet was a perfect match to a particular class of machine learning model called convolutional neural network. So, or today, neural network is renamed deep learning, but the core is the neural network technology developed in the 70s and 80s. So I'm sure some of the parents sitting in the audience might be graduate students who have done some work in neural network when you were students. But there are some names that you probably no longer recognize, like Kunihiko Fukushima, who was a Japanese researcher who pioneered convolutional neural network. And then later, scientists like Jeff Hinton, Yang LeCun have taken it a step further. So convolutional neural network are high-capacity models with a lot of parameters. You can think of it as a brain-inspired model. I want to make sure that you don't walk away thinking this is a replication of brain. There is a lot of confusion in the world out there that's saying deep learning is just a brain. It is not. The neuroscience and have told us some of the mechanisms of neural network is different in the brain, but this is a brain-inspired model. Why? Because the basic building block of a convolutional neural network is a neuron-like unit. It takes inputs from other units and sends outputs to the next unit. So that is a neuron-like unit. Also, similar to brain, it's layered in hierarchies. So just like our brain is organized by hierarchies and layers of neurons, neural network or convolutional neural network is layered by hierarchies of neuron-like units. And like I said, this is a high-capacity model. It's huge. This is a small model we use for object recognition. And the typical model like this have 24 million nodes, 140 million parameters that the machine has to learn, and 15 billion connections. And this is already nothing. This is an outdated model. The models today are even bigger than that. But this is where the great convergence happened. This high-capacity model combined with the enormous data from ImageNet, combined with the maturing of NVIDIA's GPU chip that can enable parallel computing to speed up computation, we suddenly, in the year around 2012, the entire field of computer vision, machine learning, and AI saw a renaissance of capabilities and AI achievements, started with object recognition. Here's an example of a machine was given a picture and was able to locate the cat and be able to assign a name. But you know, the life is not just about cats. And here's another example of machines the algorithm seeing a new picture and was able to locate and label teddy bear, boy, girl. Here's another example of seeing small objects even in the background, such as kite, in addition to foreground objects such as dog and person. So with this kind of progress, we are starting to see computer vision's object recognition technology maturing and being able to apply to real world products such as Google photo tagging and so on. So that was very encouraging. So far, we focused on teaching computers to see objects. So, like I said, my daughter is 14 months, and this is what she is going through as well, seeing objects and naming them. But that's only one good important step in development or in visual intelligence. Soon, children will hit another major milestone in their ability to learn, and that is to communicate in sentences, to be able to tell a small story when they see a picture. And this is what a child says when she sees this picture.
Okay, that's a cat sitting in a bed.
Here's another
Those
example.
are people that are going on an airplane. That's a big airplane.
Very cute, huh? So, what do we have to do to enable computers to say something like that? Well, we have to take the machine learning or deep learning algorithm to another step. So this time, the vision component of a model and the language component of a model have to start working together. So a couple of years ago, we developed a model that can take snippets of a visual world, for example, an object or part of a scene, and then connect it to language phrases, words and phrases it has learned in the training time, and then be able to construct a full sentence that reads like a cat lying on a bed with a laptop. So that is the combination of vision and language that can enable us to do that. And here is the example that computers can say when they see this picture, the same airplane picture that the girl just saw.
A large airplane sitting on top of an airport runway.
Right, so it's not as cute as she is, but it's telling a good story. Here's another
A
example.
man is standing next to an elephant.
So I have to say it is pretty incredible. By around 2015, our lab, among a couple of other labs in the world, like Google, Microsoft, UCLA, Berkeley, we developed the first machines ever that can speak human-like sentences when seeing a picture for the first time. Think about it. It took evolution 540 million years, and it took computer vision 60 years. So it was a pretty incredible achievement. And I certainly, when I went to grad school around 2000, I didn't think it would have come that early. So since then, we have taken this technology a bit further. Now we have developed algorithms that can actually speak multiple sentences, looking at different parts of a scene, because our visual world is complex. And we see different stories in a scene, and we're able to train algorithms to see the same level of complexity, and they can even put them together into paragraphs. Granted, they're still not perfect. There are mistakes. For example, in this picture, the computer sees two buses driving instead of a double-decker bus. So, but the progress is enormous, and we are working really hard, both at Google as well as Stanford, to drive these algorithms further. So, in short, we have successfully used neural network architecture to train computer vision models that begin to tell stories of the visual world. This is a brain-inspired perspective. So with the availability of data and the blossoming of this powerful neural network models, we're seeing as a field the unprecedented advances in all areas of computer vision, both in my own lab as well as the field in general. So I'll give you a few more examples to see a little bit the breadth of this field. Like I just said, vision is not static. Humans probably in general taking video, the biological experience is more video-like rather than static image-like. So in a collaboration a couple of years ago with YouTube, we put together a sports video data set of 1 million sports videos, and we're able to train a deep learning algorithm that can recognize 470 type of sports. And what you're looking at is on your upper left corner, the first row is the highest probable label of that particular sports that's showing. So for example, wheelchair basketball, martial arts, that's exciting. Kayaking. Sometimes it makes a little bit of a mixed whitewater kayaking. Golfing. And if you take a static picture like this, it's very difficult to recognize this is a golfing sport. So this algorithm takes into account the continuity of time and was able to do a fairly good job in this. So recently, we have taken this even a step further. It has a continued collaboration with YouTube, with Google. Not only we're able to give an overall label to the sports video, we can develop a deep learning algorithm that go into the sports and be able to track individual players. And for example, in the basketball game, not only the algorithm can track the individual players, it can actually recognize who is performing events. For example, in this example on your right, the algorithm has detected a successful three-pointer shoot and was able to find that player annotated in the cyan box who has performed that three-pointer shoot. Taking it to a different domain of vision, and sometimes we cannot use RGB data because of privacy concerns and other concerns. For example, in self-driving cars, we have depth sensors and LiDAR sensors. In hospitals, it's also important to have depth sensors instead of camera-like sensors. But we need to recognize human activity. So in this particular work we just published, my students developed an algorithm to understand human gesturing using depth sensors that goes beyond the RGB domain. And in a very similar setup, we collaborated with the European train station in Switzerland that put hundreds of depth sensors in a station and help the station to monitor 70 million passengers every year and track their behavior throughout this train station. You're looking at a top-down view of every moving dot is a passenger or customer to the train station or traveler, and tracking their movements. This gives the space and the government good data to understand many important information such as timing, the people's movement, where should we put the ticket booth, where should we put the vending machine, and so on. And recently we've developed an algorithm that can actually track more precisely human movement because of incorporating social awareness of the way humans or groups of humans behave. So not only we're doing this basic science tech research, we have recently started a very close collaboration with multiple healthcare institutions. One is Children's Hospital at Stanford, one is the Adult Hospital at Stanford, another one is the Intermountain Hospital in Utah, to put some of the computer vision technology into healthcare usage to help doctors monitor patient movements, hand hygiene practice, and so on. So in short, I've been a technologist for 20 years, and the thing that excites me the most is really seeing the potential of computer vision technology that can solve real-world problem. So that is a technologist's perspective. Last but not the least, I want to share with you one more perspective, and that's the world I live in. So 540 million years ago, the challenge of animal vision and intelligence is for the survival of the species or individual organism. Today, I think the challenge for machine vision and AI, of course, should be the thriving and better lives of human race. So an inevitable question that I get as a technologist is AI a force of destruction, or is it the hope we have for a better tomorrow? And I get that question a lot in this recent wave of AI frenzy, and here we live right in the middle of Silicon Valley, where you cannot pass a day without hearing some AI news. Well, about 3 or 4 years ago, I think I had an epiphany moment myself, and I think we should ask a different question, which is the t-shirt I'm wearing, is that AI will change the world. AI is one of the biggest driving force of the fourth industrial revolution that human race is living in. But the real question is, who will change AI? And I think this is the reason that I actually want to come here to talk to the students. So if we look at the statistics of the composition of the technologists in the world today, we really have an issue of diversity. We have a crisis of lack of diversity in STEM in our country and worldwide. So in academia, at the undergraduate level, about only 25% of women are computer science majors. Stanford is actually beating the national statistics. At Stanford, we have 30% women. Nothing to be that proud of, but we're making progress. And then by the time you finish undergrad and go into grad school, go into faculty, that number just drops. The attrition rate is very high. The national average of engineering school women faculty is about 15%, and Stanford is not doing any better than the rest of the country. And underrepresented minority is even worse. The national average of African American computer science majors or faculty is way below 15%. And in tech, it's the picture is not pretty at all. Actually, I think it's pretty bad. Major Silicon Valley companies we list here have very low percentage of women engineers or underrepresented minority engineers. And this is taking into consideration of all ranks. If you go up higher rank into the especially executive level, we just see very, very few women or underrepresented minority. And I think this is an issue. About 6 months ago, White House had the Obama White House had had a conference talking about the frontiers of technology, and I was on a panel specifically talking about the issue of diversity in AI and advocating for this. And I think this is not just to have more girls, have more underrepresented minority. We really have major reasons we want to invest in the pipeline of technology. First is for economics and labor reason. Computer science is a blossoming field. Especially here in the heart of Silicon Valley, we know this technology is going to transform every single industry. Here we tend to see, web-based industry or social media or transportation. But if you think about agriculture, education, healthcare, government, manufacturing, oil and gas, every single industry is being transformed by computing, by AI. And we need more labor force. And if we don't include everyone, we're missing that. And if U.S. is not including everyone, we might be losing the global competition. It's also for creativity and innovation reason. There's numerous studies done by many, many researchers in sociology, in psychology, in business school that shows that when you put a diverse group of workers together in a team, the solutions they come up with is more innovative and more creative. The process might not be the most comfortable, because when you are with people that are like you, you have more, you're more comfortable. But precisely because of that discomfort, it challenges everybody to come up with more innovative solutions. And finally, it is for social justice and moral values. Starting with data, when data is biased, the algorithm is biased. Just typing the word grandma in your favorite search engine, image search engine, you see the bias there, the race bias or the age bias. So starting from that point on, machine value is human value. There's no independent machine value. We are, as technologists and leaders, future leaders of the world, we need to think about what technology we're building, because we need to really invest in the technologists who are building this technology. So I've been really so the development of vision and intelligence resulted in a Cambrian explosion of the diversity of the animal species 500 million years ago. Today, what I believe is by including more people in the development of AI and STEM will set off a Cambrian explosion of the technology solution that human society needs. And for doing that, I want to specifically offer one important hypothesis, is that in the education and research of AI and STEM, we need to include a humanistic message and mission statement. AI, STEM is not just about being cool, wearing hoodie. It's about giving a mission for the technology that will help the human society. And that is the perspective of an educator and a mother. Thank you. So what do we do?
So now we'll just be moving into the Q&A session for approximately 15-20 minutes. We'll be taking questions from Slido. So the first question is, recent literature has focused on enhancing the interpretability and data security of computer vision systems. Where do you think this field is headed?
Is this a question from a parent? Very good question. I think one of the most intriguing development of the deep learning revolution is that the models have becoming so humongous, it's really difficult to interpret. And I think this is fine if you just want to tag a cat or a chair in a picture, because the stakes are not that high, right? Like if you make a mistake in your Google photo tagging, that's fine. If your product recommendation is not perfect, that's fine. But this will become a serious issue if we cannot interpret our models if it's in, say, healthcare condition or financial services when fraud is detected, and so on. So, in the field of AI and machine learning and computer vision and natural language processing, all these related fields, there is a very strong push of interpretable models or explainable AI. And this is really trying to not only continue the strength of deep learning to be able to perform really well in these tasks, but be able to offer insights. So it's a very early area of research. As a field, collectively, we haven't done a too much to offer the final solution yet. But just as an example, in computer vision, now a lot of the algorithm is not only just tagging pictures, but really trying to explain the different parts of an object, the potential interaction points of the objects. These are all part of the effort for interpretable models.
And the next question is, do you believe that unsupervised learning is the best way to teach computers to see?
So that's a great question. So unsupervised learning in the field of machine learning is one form of learning. In fact, most of 99% of the major success of the last wave of deep learning is supervised learning. What it means is that during training time, the computer is giving the data as well as the correct answer to the task. For example, in ImageNet recognition, the computer is trained with the image with the tag of cat or chair or dog. So supervised learning has done very well, but there has been a decades-old exploration into unsupervised training because humans don't do everything supervised training. A lot of the baby development is through its own exploration, or what you hear about AlphaGo and reinforcement learning. So I do believe unsupervised learning is a very important sub-area, but I also think there is many different types of learning: reinforcement learning, semi-supervised learning, active learning, curriculum learning. So unsupervised is one of them.
Next question, how do you think computer vision can directly help people who are blind or visually impaired?
So I think there has been technology effort of computer vision to help the visually impaired since the day computer vision was born. So a lot of potential is, once there is an area of computer vision I didn't talk today at all about is 3D vision, is understanding the 3D geometric layout of the visual world and objects. And you can imagine that technology can help navigation and manipulation. And then, of course, recognizing texts, labels, a situation. These are all basic technology that we can help the visually impaired. One thing I think that's exciting coming up in this era and going forward is the combination of basic vision technology with AR, VR, with brain-computer interface. So to deliver the basic science result of computer vision to visually impaired patients, we need more than just vision algorithms. We need the actual physical deliverable devices. And with depending on the specific scenario, AR, VR is one way to deliver that. Brain-computer interface is another way. So I think there is exciting work to be happening soon.
As AI becomes more embedded in our everyday life, what do you believe are the largest ethical issues in computer vision, and how are we working to address these?
So like I said already, so I think the ethical issues in vision and the ethical issues in AI are extremely intertwined. The bias can be everywhere, right? From data to the way algorithms are trained, to the way that the social impact, the labor impact of automating machines. We have layers and layers of issues, and also it's the human interaction in all aspects of the society is not just only task focused. It also has a dimension of emotion, social communication, compassion, and so on. So my view is that this is a topic that the whole society should participate. This is a topic that not only technologists need to pay attention to, but educators, policymakers, law enforcement, economists, and media all should participate in this conversation.
Okay, we'll take our final questions. What do you think are some of the most powerful applications of computer vision?
Some of the most powerful applications. First of all, just because the brain spends more than half of our cortical function in vision tells us vision is so universal. So a lot of you hear about self-driving car. I would say that without the 30 years of computer vision since the 80s that's spent in 3D reconstruction, object recognition, we wouldn't have self-driving car technology today. So already you're seeing that the core technology in self-driving car is changing the face of transportation. Another area that I pay a lot of attention to is healthcare. The number of images that radiologists today have to review every day has increased something like 100-fold in the past 10 years. But we do not have 100 times radiologists in our country or in the world. So assistive diagnostic technology of healthcare would be phenomenal to help in medicine. And this is not just about making lightening the workload or helping the accuracy of radiologists. It's about distribution of resource as well. While we all here collectively live in one of the most affluent part of our country and world, there is a huge bulk of the world that don't even have access to basic healthcare, and computer vision can do a lot. And one last example is government can use a lot of computer vision technology. We are seeing satellites, private satellite companies sending out satellites to collect a lot of images. Just recently, a Stanford professor published a paper of using satellite imagery to track poverty in Africa. And these are the regions that there's no road, there's not even running water. The government, and it's in constant conflicts. It's very difficult to send human inspectors to go to those regions to understand what is going on in that society. And imaging technology with satellite imagery can help can help policymakers and the government think about resource and so on. So these are just examples. There's endless examples of computer vision applied to our world.
Okay. Thank you so much, Dr. Li, for your wonderful presentation. I'm sure that we all learned so much and are so inspired by your work, not only in computer vision, but also in advocating for diversity in STEM and AI. We are incredibly honored to have you at Symposium, and thank you so much for joining us.